Okay, we're going to continue with the next talk. So it's a pleasure to introduce Michele. Michele received his PhD from Bocconi University in Milan, worked in Duke University and MDA Anderson in Houston, and also in the University of New Mexico. He recently moved as a professor in the Department of Statistics in UC Irvine in the States. Michele has worked in several fields of applied Bayesian statistics, including genomics and imaging. And today he's going to talk about two-group mixture models for multiple testing, a Bayesian nonparametrics perspective. Okay.
Thank you, Andres. I would like to thank the organizers for having me here today. So today, as Andres introduced, I'm going to talk a bit about a type of modeling framework which is common in the analysis of high-dimensional data for multiple testing, but goes under the name of two-group mixture model. First, before I start, though, I'd like to thank actually the people that have worked with me and that have done the greatest part of the job. My students, and in particular, today I will discuss some work that I've done with Francesco Denti at Bicocca University, Milan, Italy. He's gonna take over a postdoc position at UCI with Babak Shababa in a few months. And he has been working with me, Antonio Lihoy, and Fabrizio Leisen on what I will present in the first part of the talk. The other two guys are already assistant professors, Alberto Cassese at Massey University and Weishuan Zhu at Xiamen University. They are the ones that are the main contributors for what I will discuss in the second part of the talk. So as I mentioned, what I'm going to discuss about is a modeling framework which has been popularized by Efron with two landmark papers in 2006-2008. The modeling framework is pretty simple. The idea is that you have some different scores, some test statistics, and you have a large number of distinct hypotheses in what you may consider a high-dimensional data framework. Each score, each statistic, is assumed to be drawn from a mixture distribution of a null component and an alternative non-null component distribution. There is, of course, a mixture weight which has to be between 0 and 1. Efron, the first point that Efron makes is that if we follow theoretical mathematical statistics discussion, so F0 is assumed to be, should be a standard normal distribution in most cases. So this is what it refers to as theoretical null. In reality, the true null distribution may differ from the theoretical null, and that may happen for many different reasons. In particular, the limited sample size or the fact that we do not account for some correlation that should be accounted for in the modeling framework. So Efron's solution is to estimate what he calls an empirical null distribution. And his framework, his modeling framework, assumes two important hypotheses. I mean, it does estimate the empirical null distribution in many different ways. Let's say that two main ingredients of the different procedures that he proposes are the following. On one hand, he wants to somehow propose a good approximation of the mixture density, F. In particular, the main approach that he follows is to assume a quadratic behavior of the log density or log mixture density around 0. And the second big assumption that he makes is what he calls a zero assumption. That's basically the idea that under the alternative, so the alternative should not pass, it should not put so much mass around zero. So the main mass around zero should come from the null distribution. So when we look at this framework in a Bayesian perspective, of course, one may think about putting prior models on F0 and F1. And the most common way in which this has been done in the literature is by using or assuming that F1 and F0 are realizations from a Dirichlet process. And indeed, there is a wide literature that has been proposed to that try to model either F1 or F0 or both as realizations of the Dirichlet process. I'm going to put here just a few examples. The first one and the most relevant I see at the beginning at least was a paper by Kim Do and Peter Mueller in 2005. And of course, what we did is just to consider, instead of a mixture of F0 and F1 with parametric form, just a mixture of two Dirichlet processes. They applied these to the analysis of gene expression data, so high throughput framework. James Scott, in an analysis of applied statistics paper, basically modeled the autoregressive parameter in time series using the same idea of a null model versus a non-null model. We have also other papers by Scarpe and Danson where F0 is parametric and F1 instead describes a non-parametric contamination for functional data. A very close approach to the one that we're going to follow later on, discuss later on, is the one by Martin and Tockar, and they basically assume F0 parametric, concentrated around the 0, and instead F1 a semi-parametric mixture. I also have worked on this type of models before, for example, for modeling count data. So this is just to say that this approach of modeling or assuming for multiple hypothesis testing a mixture, a two-component mixture, a two-group mixture model, is quite ubiquitous in the Bayesian literature. Now, let's see why this is ubiquitous in the frequentist and Bayesian literature. Well, on one hand, the reason is because this type of approach is amenable to a nice setup in terms of decision framework. In particular, Efron proposes what he calls the local FDR, and for each hypothesis, it basically estimates what it is effectively for this hypothesis, the possible probability that a different score Z is generated according to the null hypothesis. And whenever this local FDR is less than a given threshold alpha, it basically selects these hypotheses as relevant or significant. The observed score is significant. So, and this procedure is shown to control the Benjamin-Hochberg FDR at level alpha. Now, in a Bayesian setup, what one may want to do is instead to consider the problem in terms of a loss function, which compounds expected false positive and false negative decisions in some ways. The optimal decision rule in this case is simply to threshold the posterior probability of alternative. And this can be done also to control at some level a measure of false discovery rate. In particular, it is possible to show that by thresholding or by choosing the optimal rule by thresholding the posterior probability of alternative, you actually can control the marginal positive FDR in the case of independent hypotheses. Now, a somewhat alternative procedure that has been used in the Bayesian parametric literature is what is usually called a spike process. I would like to point out the differences between the idea of putting a Bayesian parametric prior on F0 and F1 directly, and an alternative idea, which instead puts a mixture on the base measure of a Dirichlet process. In the literature, this type of modeling framework is also very popular. It's been popularized in particular in the modeling selection literature Bayesian model selection literature by a work by Kim, Marina Vannucci, and David Dahl in 2009. They define a spike Dirichlet process for hypothesis testing and variable selection. Here, in this case, they assume F0 simply being a point mass at 0, and this is what they call spike slab Dirichlet process prior. More recently, Canale, Prunster, Lihoy, and Nipoti, they have introduced the spike two-parameter Dirichlet process, spike Pitman-York process, if you want, and they have basically shown that in this case, for this type of modeling procedure, it is better to use a spike two-parameter Dirichlet process with respect to a simple spike DP. In this talk, I would like to investigate a bit more the use of a two-parameter Poisson Dirichlet process in lieu of a simple Dirichlet process when you are confronted with a problem of hypothesis testing using a two-group mixture model framework. Fernando Quintana on Monday has discussed already the main features and main characteristics of the Poisson Dirichlet process. I'm going to just recall a few of them, and I will point out a few aspects that will be important, I think, to try when we try to use this type of models for hypothesis testing in the two-group model framework. So a two-parameter Poisson Dirichlet process can be described as simply as an infinite mixture where the weights follow a stick break representation with beta random variables that depend on two parameters, sigma and theta. Sigma has to be between 0 and 1, so it is bounded somehow in the values that can achieve, and we will discuss about these values a bit, and theta has to be greater than minus sigma. The random probability measure has atoms yk, which are assumed to be IID from a base distribution, P star, base measure distribution, which can be seen as representing the expected value or centering distribution of the random distribution P tilde. So, a characteristics of this type of models, Dirichlet process, two-parameter Poisson Dirichlet processes, of course, is that they induce clustering because of the positive probability of ties between samples from the processes, right? So this is one of the reasons why these type of processes are used in statistical applications, typically to model heterogeneous populations. In the type of clustering, like Fernando discussed in length on Monday, the type of clustering can be described by what is called the exchangeable partition probability function, which basically characterizes how the samples are going to be allocated in 2K different clusters with assumed sizes N1 and Nk. And from this expression, we can see that the partition, the probability of partitions of that we can generate through the two-parameter Poisson Dirichlet process depend essentially on the two parameters theta and sigma, which is expected, of course, right? But let's look in particular in this representation at the effect of sigma. So, as I mentioned, the values of sigma and theta affect the clustering structure of a two-parameter Poisson Dirichlet process, and there are very many different ways in which we can see this. One possibility is to look at the prediction probability function, according to what Fernando said on Monday. So basically describing the predicted distribution of a two-parameter Poisson Dirichlet process. You can see from this predicted distribution formulation that if sigma increases, if sigma gets closer to 1, it's more likely to get observation from P star instead of observations or samples that coincide with one of the previously observed samples. Can you hear me well? Perfect. So, in other words, values of sigma which are close to 1 are going to favor a large number of clusters, and many of these clusters will be singletons, because we will be extracted from P star. On the other hand, sigma also characterizes the variability of the realizations from a two-parameter Poisson Dirichlet process. In particular, we can see that when sigma becomes close to 1, basically the variability becomes lower, right? So the process is going to concentrate quite tightly around the base measure P star. So this is basically saying, in other words, that any sample which is drawn from a two-parameter Poisson-Dirichlet process with high sigma is going to have basically characterized by, let's say, an empirical distribution of the samples, which will have lots of weights of similar size, and the empirical distribution of the samples will be somehow closer to P star, the base measure. So let's go back to the two-group. No. The intuition here is that if you let based on this representation, if you let sigma increases, you're going to have lots of singletons, right? So many weights will be more or less of a similar size. Mm-hmm. So now let's go back to the two-group, two-parameter Poisson-Dirichlet process model. Here we want to basically characterize the distribution of F0 and F1, right? A null component and an alternative component. What we've seen before in these slides about the effect of sigma basically can suggest somehow to use these properties to set P0 and P1 in some smarter way than just putting Dirichlet processes in one or the other, right? So think about the properties of a bit measure process and try to act accordingly on that. So in the general model, of course, can be rewritten by considering an indicator variable, gamma I, which is extracted by Bernoulli with parameter rho, and according to the value of gamma, we are going to have a Poisson-Dirichlet process model characterizing the null or the alternative distribution. So we are going to have a Poisson-Dirichlet model, two-parameter Poisson-Dirichlet model, either characterizing a P0 tilde or P1 tilde. Now, the parameters of these processes have to be chosen carefully, but the characteristic of the model that the partition functions that the partition that we can create for this model are actually quite simple. In particular, we can characterize the exchangeable partition probability function for the sample from the mixture density that we just described. And here, what we can see is, in particular, that the two respective partitions, random partitions, are independent. So this is, of course, telling us simply that we can, once we have divided or the samples in P0, in samples coming from the null or the alternative distribution, we don't have to worry too much. We don't have to worry about the possibility of, let's say, overlapping clusters. Indeed, the probability of having a sample, having observations coming from the same process, let's say, of two different valued observations coming from different processes is 0. So this is just telling us that we don't have to worry about any possible overlapping between the clusters. Okay, so in terms of a two-group modeling perspective, though, so how are we going to fix the parameters of the processes for the null and the alternative component? On one hand, we want to have the null component somehow mimicking the true null distribution, let's say. So if the true null the theoretical null distribution is a normal 0, 1 as a general setup idea. So P0 tilde should concentrate around the true null distribution, and in particular, we want to do a better job in a quite good job in estimating these true null distribution. So the suggestion here is, well, first to have high values of sigma, to consider high values of sigma when we want to estimate P0, because based on the conclusions that we reached before, we expect these high value of sigma to give rise to many samples, right? And to be somehow closer to the expected theoretical null. we are much more free to model the alternative distributions. So in general, we should expect indeed the alternative distribution to allow quite large deviations from the null distribution. So in this case, we would like to expect a sigma 1 value, which may be lower, possibly even close to 0, with respect to the null distribution. So this is just to say, if you want to use a two-group mixture model in a Bayesian formative framework, just using two-Dirichlet processes per se may be simplistic or naive, so we should somehow think about what we can do to improve. And of course, what we actually have in practice most of the times is indeed a Dirichlet process mixture framework, by which the two-parameter mixture model actually characterizes the prior of a kernel, as usually assumed normal, which describes continuous observations. So the second point that Efron was making, if you remember at the beginning, was that there should be a zero assumption. In other words, the mass of the null distribution should be close to 0, whereas the mass of the alternative distribution should be far from 0. So we want, similarly, to achieve separation between the null and alternative hypotheses in this framework. And one way we can do this, well, first is to set up a good base measure for the null model, right? We want a base measure in the null case to be somehow very close to the theoretical null. And we can do this by setting appropriately the parameters of a normal inverse gamma formulation. On the other hand, we want the mass of the alternative distribution to be far from 0. And to do that, we can, well, on one hand, consider a bimodal mixture of normal inverse gamma distributions for the alternative. These mixtures are bimodal and will depend on a location parameter M1 here. So the importance of the location parameters in this type of mixture model is well recognized. In order to make sure that the mass of this bimodal mixture is going to be far away from 0, we also add an additional component to the game, which is basically assuming that M1 comes from a non-local prior. So non-local priors have been used, especially in the Bayesian model selection literature, to allow, basically, for priors that assign vanishing small density to small neighbors of the null hypothesis, and assign most of their mass far from the null hypothesis, from the parameter space defined by the null hypothesis. So, in particular here, we are going to use what's called a moment prior, a art moment prior for M1. And so the combined use of a non-local prior and the two-parameter Poisson Dirichlet framework with sigma 1 and sigma 0 chosen carefully, we hope that this framework could help us in improving the operating characteristics of the testing procedure. In order to obtain these operating characteristics, of course, we have to do a decision at the end of the day, and we can easily obtain and conclude and take decisions based on the MCMC output. Now, we did a few scenarios, right, to try to evaluate the characteristics of this proposed method. I'm going to show basically just the last two. These scenarios basically correspond to different types of masses expected around 0, right? In particular, the fourth one, the scenario 4 should be skewed in the sense that there is only mass mostly I mean, it's a case in which you expect very skewed distributions with actually a scenario that was taken from the paper of Martin and Totker. Scenario 5 is peculiar because the alternative is very simple, but for scenario 5, we are expecting that the F0 actually is is not the usual normal 0, 1, it actually has larger, heavier tails. So it's kind of a departure of the model from the idea that the theoretical null should be standard normal. So in terms of results, the results are quite interesting for different reasons. First, one can show that results kind of became, one can show that the idea of having a higher sigma 0 with respect to sigma 1 actually leads to good operating characteristics in general. I didn't show this here, but if I do the opposite, I put sigma 0 less than sigma 1, the operating characteristics quickly degrade. So in particular, it looks like the best results is obtained in general when sigma 0 is high, but not too high. It's not 0.9. There is a reason for this, and it's probably also better to consider these type of values for computational reason because of the amount of singletons. You have to expect that in your hypothesis testing, around 90% of the samples will come from the null eventually. So you want to somehow create some sort of clustering even in the null model. And sigma 1, I mean, it's kind of very difficult to make a decision here, but it's somehow, if it is not exactly 0, maybe it's okay, and you know, it's fine to somehow give it a bit more, a bit less, a bit more ability to explore the parameter space. Which is interesting, though, is the comparison with other approaches, and I would like to point your attention to this one in particular. This is the DP mixture. This is just obtained by just setting in the MCNC sigma 0 and sigma 1 equal to 0, right? So there is still the contribution of the non-local prior in this type of model, right? Still, the operating characteristics for the DP mixture model is quite worse than the two-parameter Poisson-Dirichlet model. So the fact of choosing sigma 0 and sigma 1 in a proper way actually makes somehow sense, or at least looks like it's making sense. Another important aspect is Benjamin and Dockber. Benjamin Dockber procedure is very hard to beat. It's actually pretty good, right? It makes, the issue with Benjamin and Dockber, however, is that it assumes that the theoretical null is indeed normal 0, 1. So if there is any departure from the normal 0, 1 model, for example, like in scenario 5, the operating characteristics of the Benjamin and Dockber procedure is going to decrease quite sharply. So again, these are things that one can consider, and of course, these other methods are other Bayesian parametric methods that we discussed before. Finally, for a simple example, well, we did use, among others, a data set which is also used by Efron. And here this is a prostate data set with 6,033 genes for 102 observations. 52 are from a prostate cancer patient and 50 from a healthy man. And when we run our model on this data set, well, we see a few things. First, that the Benjamin and Dockber procedure at 10% FDR already flags 3,572 genes, 725 genes, which is way too much, right? The local FDR and our model at the 20% level FDR, which is the one recommended, by the way, also by Efron, basically flag a much smaller number of genes. So at the end of this, the first takeaway point that I would like to make is that the way in which one models the Bayesian parametric prior in the two-group mixture modeling framework actually has to be carefully thought about. And it's very easy and it's very immediate to think about the most common Dirichlet process model to use, but this may not be the best way to go about it. The second point that I would like to make today is what to do when we go from a setting of independence to a setting of dependent hypothesis, which is actually quite common. In particular, one can think of dependent hypothesis in settings like neuroimaging, which is one of the application areas that I work with. In that case, you have data that collect time series responses of individual brain activity over time at different locations in the brain. And you want to understand which area, which voxels in the brain are active at a particular time in a particular voxel or region. The second example is actually the one that I'm going to discuss about, and it is an example that uses CDC data, which have been collected weekly by the Center for Disease Control and Prevention of the United States about pneumonia and influenza mortality in the 50 states, contiguous states of the US. So in this type of data, what you are interested in is to detect outbreaks of influenza over time, and you have a time series for different states. So from a modeling perspective, what you have is, at the end of the day, an hypothesis, multiple hypothesis testing framework over time and space. With hypotheses that are, of course, dependent, because you expect that there is an outbreak in California, probably there is an outbreak also in Arizona, right? And you expect at the same time that if there is an outbreak on November or December 4th, right? Probably there's going to be an outbreak also next week, right? So from a particular modeling perspective, one has to consider how one would model this type of situations. And in spatial-temporal statistics, the type of model that is typically used is a random effect model that assumes that the measurements collected at different locations at different times are realization of a spatial-temporal process that is usually characterized by three different components. One component which is a general regression term, one component which is a pure random effect that captures deviations from the general regression term that can take into account usual covariates. We may not know the covariates that specify the pure random effect, and also a regular measurement noise. From the perspective of a two-group model here, what we are going to consider is typically the pure random effect, the spatial effect, spatial temporal effect in this case. And what one may be interested in is to study this type of hypothesis. At time t and location s, our process is in indifference region, corresponding to the normal region, or not. And of course, at each time and at each location, we have a true state of nature, which we don't know, and we have a decision to make based on our estimation procedure. So if here, with the type of decision that we have to make and the type of problems that we have to assess can be somehow tricky to work with. In particular, I would like to point out two possible ways in which an idea of false discovery can arise in the spatio-temporal literature. On one hand, there is the idea that one can test hypotheses at individual locations or time points. And in this case, if you're interested in what happens at each particular time and location, naturally, the type of false discovery conceptualization that you are thinking of is the false discovery rate. And you can define false discovery rate basically based on the number of false positive and false negative outcomes in a region and over time. at that time. And of course, this can be done in different ways, but also there is also a notion of cluster-wise inference in this type of problems. So one may be interested in assessing the ability to find clusters of observations and clusters of time points that are in outbreak. And this usually allows, I mean, the cluster-wise inference usually allows to detect, to obtain more powerful procedure because you can take into account the correlation over time and space. And a major point of discussion in this case is the definition of cluster. In some cases, the clusters are given. For example, the states, right, define clusters, right, at some level, which are given by, let's say, the data set. In the neuroimaging application, for example, you can think of clusters as aggregation of voxels. And while there are regions, brain regions that are defined, one may usually want to cluster over space in a more direct way from the data, right? Instead of impose notions of clusters in this case. So this is a peculiarity that has to be taken into account, but still at the same time, one can obtain a notion at this point of false cluster rate, and also similarly one can obtain a notion of missed cluster rate, misclassification rate. And the goal usually is to control the false cluster rate while minimizing the miscluster rate. All these, both this problem can also be solved, let's say, or from a statistical perspective, confronted with from a decision problem. I'm going to focus right now just on the individual location problem. And again, we have a loss function that combines a weighted sum of false positive and false negative counts in space and time. And again, one can show that also in the space and space-time situation, under mild conditions, in particular in monotone rate conditions, the same rule, decision rule, optimal decision rule that we discussed before applies. In particular, the posterior expected loss is minimized by thresholding the posterior probability of the alternative at that location and time. And again, the particular threshold can be chosen to control the Bayesian FDR at a particular level. Now, let's go back to the two-group model. And in this case, again, the issue is to try to clarify or model F0 and F1 in appropriate ways. Here, F0 denotes a null process over space and time. This may be in a normal state where there are no outbreaks of influenza and pneumonia. And F1 may be instead an alternate process which describes fluid-related mortality during outbreaks. Here, the issue with this type of model is clear because, well, while there is a variation over space and time of F0 and F1, what we miss here is variation of the probabilities W, right, of choosing F0 on F1 over time. So one eventually may want then to have a selection indicator gamma ST that with some probability W that may change over space and time, right, is indicating if we are in the null process or in the alternative process. Now, easy to do, easy to think about, and one thing that one, from a Bayesian probability perspective, one thing that one could think about is, for example, having a omega ST that changes with space and time, and then F0 and F1 Dirichlet processes. Very easy. Issue with that is F0 and F1 are realization of Dirichlet processes, so they typically describe an exchangeable samples. So basically, the samples are exchangeable, right? So the basic idea behind the Dirichlet process is that any sample, any realization of the Dirichlet process is describes, exchangeable random variables, right? So in space and time, exchangeability is not that reasonable. So also, we want to have a process that allows us to cluster in a meaningful way, at least over time, and possibly also over space, the realization from the random spatial effect. So, what we want to do is to characterize a mixture model formulation at each time point, condition of the past, for example, to start with, and in particular, to consider a realization of a sequence of conditional distributions such that what happens at time t at location s is going to depend on what happens at previous time points. And we can do this by, again, using, in this case, a two-mixture group formulation, which is time-dependent and possibly also spatial-dependent, by which the selection at time t can be either from with some probability, driven by the process gamma st, with at time t location s, we can either be in the null process. For simplicity, for now, we can assume theta st being just 0. Instead, when gamma st is equal to 1, theta st is going to come from an alternative or slab process that describes the temporal dependence of the process. So when you are in the outbreak, you're actually interested in the temporal dependence of the outbreak. So from a modeling perspective, you can describe these also as a dynamic spike slab prior, because we are assuming at this point that theta 0 st is just a point mass at 0. Okay, so now our attention should be then in trying to describe the temporal dependence of a process through the process gt-1, and in particular, this can be done in different ways. Fernando, I think, at the end of his talk, described partitions evolving over space and time. I still have to think through all what it did, but yeah, I think that probably also his model could be seen in this type of representation as well. In particular, remember there was also an indicator in Fernando's case. So what we want to do in our case, we want to describe how the process, the alternate process, can cluster observations over time. And we want also to somehow describe the persistence of a state for some time at each location. And we want to do this in a Bayesian parametric way by describing the alternative process basically via a generalized species sampling sequence representation. What we're going to use is the toolbox offered by what are called conditionally identically distributed sequences, CID, which have been proposed first by Berti, Fratelli and Rigo, Bassetti, Leisen, and Grimaldi in 2004 and 2010. And the idea here is very simple. We're using a predictive probability function formulation, as in Fernando's talk, but what we have is a prediction probability function that changes over space and time. In particular, in this case, only over time, to be honest. But the main point here is that at each time t, we can have some probability of ties with some previously seen levels of the process, so we have some probability of ties, or instead, we can get our the observation, the realization of a random process at time t from a previously unseen levels generated according to the base measure G star. Now, the main difference between this approach and what Fernando has done, as presented on Monday, is due to the weights. In this case, the weights are time dependent and possibly also space dependent. So the framework of CID sequences has been studied quite a bit in the Bayesian parametric literature by a few people, in particular, as I mentioned, Berti, Fratelli, Rigo, and Fortini, Petrone, and Sporisceva in 2016. Sonia Petrone has also been working more recently in characterizing the asymptotic distribution of this type of sequences. The basic idea here is that a CID sequence can be seen as a relaxation of the hypothesis of exchangeability. In particular, an exchangeable sequence is for sure CID, but the converse is not true in general. What is missing is basically the presence of stationarity. In particular, you can think of the CID sequences as sequences that ensure stationarity in the future conditional on the past. Francis, pass me that. And asymptotically, indeed, it's proven that the CID sequences basically are going to be describing asymptotically exchangeable sequences. I mean, to be more precise, functionals of these CID sequences are going to be corresponding to functionals of exchangeable sequences in asymptotically. Okay, so now how can we describe or how can we model this type of objects with weights that change over time? There are a few suggestions in the literature, in particular the generalized Ottawa sequences framework by Bassel, de Grimaldi, and Leisen. Basically, they suggest that a quick way to allow these guys to depend over the time points is simply to introduce some latent random variables at each time point, W1, W2, that can be seen as marks that drive the sequential random allocation of the observations. In particular, so at each time point, t plus 1, for example, there is a positive probability that depends on the previously observed realizations of theta and the corresponding marks to basically have a tie between theta t plus 1 and one of the previously observed values. And similarly, there is some random probability that the next value of theta is going to come from the base measure. So, in other words, the marks W1, W2, WT that come with each observation affect the probability of selection. Another way to see these is basically to think at the Chinese restaurant representation of a digital process and think that it's not only the table that matters, right, but even some characteristics of the subjects at the table, unknown characteristics, latent characteristics at the subject of the subject of the subjects at the table that drive their location. So this is a general framework and can be specified, for example, in two different ways. One is the use of a CID Pete major sequence framework. And in this case, what we have is weights, P as T minus 1, that depend not only on parameters A and B, sorry, before these were theta and sigma, but also on random variables W that change, that arrive at each, they describe and characterize each prediction function. Another simpler way, if you want to, or statistically more convenient way to introduce these random variables is to think sort of a stick breaking construction for weights, which depends on beta random variables. And basically you have a different stick breaking, sort of, at different time points, which are driven by these W's. And this is a framework that we have been already studied, and it's shown that we showed that actually it was a good flexible framework that provided a way to describe dependence, right? Over dependence of the observations of the time series, let's say, more flexible than digital process, Markov, and Markov switching models in some applications. Yes, I'm going to be fast. So the other point is introducing spatial selection, and we can do this in different ways. We can do this also imposing the spatial selection somehow in the weights that derive the beta-Gauss sequence, But it's much easier to actually separate, from a computational perspective, the space and time characterization in some ways. So in this way, we can be lazy and use known techniques also for computational purposes. So one way to introduce spatial selection is, for example, to use Mark random field priors. Okay, other interesting point is that we're going to basically have a spatially zero-inflated CID sequence at each time and at each location marginally, so which is kind of nice. Let me go back to the application quickly. So this is, again, the application on the CDC data, which are collected weekly by the Center for Disease Control and Prevention of the United States. What they do usually when they analyze this data is to use a very simple model, which is basically fitting a baseline yearly regression line to basically obtain like just a overall threshold by which if at some point you see a value which is higher than this baseline, you flag it as a detection, otherwise not. There are, of course, more sophisticated methods. For example, a method by Martinez, Benito, and others that use the hidden Markov switching models to identify and cluster epidemic periods over time. We're going to compare with the model used by the CDC, this model by Martinez, Benito, which actually worked pretty well. But also we were interested in comparing our approach with approaches by Kim, Van Nucci, and Dahl, that were using a spike Dirichlet process, and the approach by Canale, Prunster, Lioy, and Nipoti, that were using a spike Pitman-Yor process. So these are the data. We cannot see much, except there is some sort of more gray areas coming toward the end of the year, right? Across all the US. This is the time where you are getting probably close, it's easier to get some flu, so be careful, especially if you live in the northern areas, right? In terms of the detection of the outbreaks from our model, so we can see the map toward the end of the year 2012, where we have initially sporadic outbreaks and then a more complex pattern and a widespread pattern of outbreaks over space and time. Now, a few things to look at. So in terms of temporal dependence, the CDC model compared with our spike CID model is, of course, prone to many false positives. Of course, it's not possible to see false positives from the data. Based on simulation, we can argue that this type of spikes that we see, the detection from the CDC model that we see here could be most likely false positives. Let's see instead the difference with respect to a Bayesian parametric prior in this case. And this is a bit more subtle. Let's see if I can do this. I'm using, let's say, big, no, I cannot do it. Okay, so if I could zoom this, what you see, let's see, probably this is evidence. So here we have our model, which is the black dots, compared with the spike DP. And the spike Pitman-Yor prior behaves the same. You can see here that there is an outbreak, and then which is detected by both, and then over time, our model detects a series here of the outbreaks. Here instead, you have some time before the outbreak is detected again by the DP process, then another one which is not detected by either, but it's not detected by the DP, but detected by us, and another one which is detected by both. So this is just to say, basically, it's important to take into account temporal correlation matters, and in this case, based on our simulation and everything, we basically thought that this type of behavior was due to the fact that one model takes prediction, in the prediction takes into account the temporal dependence, another doesn't. Okay, and similarly, we do quite well for spatial predictions. Well, conclusions. So what I presented here today, I try to make an argument for a thoughtful use of Bayesian parametric priors in a two-group modeling framework for multiple testing. On one end, while the independence case is well studied, the dependent case is, I would say, less studied, at least in terms of multiple testing consequences, right? One thing that we didn't think much when we did even our spatiotemporal analysis was the issue of separation. What does separation means when you cluster space and time? We didn't think much about this because actually we put our thoughts under the rug. At some point I told you, oh, let's put theta 0 st equal to 0. Nobody yelled at me at the point, but actually that was a quick way to put things under the rug. It's much easier to deal with the null process, which is 0 overall, right? The null process also varies with space and time. So how do you define cluster and separation of a space and time? It's something that I think deserves some attention. And then other types of complex spatiotemporal dependence can be modeled. One may want to know which of the two models is actually describing a faster evolving process, right? So in this case, the multiple testing framework is probably should be considered on a gradient of spatiotemporal processes. And other things, I didn't tell you anything about the computation efficiency. We are comparable in general with the typical Bayesian parametric priors, which is bad. So one may want to look at scalable and fast implementation, especially the spatiotemporal characterization that I discussed. And as I mentioned in passing by, I think the partial steady sequences provide further modeling flexibility that should be exploited in some way. So, I don't know, that's it. And thanks again to my collaborators, of course. In what sense?
In the sense of the control you're doing, right?
Oh, okay. Well, so there are a few hypotheses that are behind this structure. So first, when the sample size increases, right, in this regard, right, I mean, you have the number, you can think about n as the number of hypotheses, or instead the number of samples, right, that gives rise to the statistics, right? So if you look at the number of hypotheses that increases, right, what happens, you have the usual assumption that you have for multiple testing. On one hand, you want to control the FDR, right, on one hand, right, at 10%, for example, 5%. So that's, in terms of this characterization here, the other big hypothesis that you make is that most of the observations are going to come from the null component. In particular, this is common. I mean, even Efron in his modeling framework is saying that the local FDR is assumed to work well when you have at least 90% of the true hypothesis being null, right? Similarly, I think here, I mean, it's gonna work better, right? And it's gonna be easier if you have a big chunk of the statistics that are gonna clearly define the null distribution. So that's an underlying assumption underneath the setup of the priors also here. So you are expecting that at least 90% of the observation will come from the null, which is expected usually when you do multiple hypotheses. Does that answer the question?